Hi everyone, this is a solution overview for part 3 of Lab 1, and in this part what we're doing is merging parts 1 and 2, so you won't be changing any of the code within the slave peripheral module or the SRAM controller module. You will just be changing the top level module where those modules are instantiated. So what we are effectively doing is adding in the SRAM controller to this block. And obviously in turn that would connect to the SRAM chip. And if you wanted to, you could even add in the 7-segment display module if you wanted to check the values in the slave registers. And this would in turn connect to the hex displays. Okay, so the thing that you are most concerned with is how to develop this logic that will allow the signals from the external bus to be switched between either the SRAM controller or the peripheral on external bus. The other thing that you will be changing is the address space for the external bus. It's going to be going from 512 kilobytes to 1024 kilobytes now. So now that you have that double in address space, you will be assigning the SRAM controller to the lower half. So the addresses from 0, 0x7, FF, FF would be for the SRAM controller. And for the slave peripheral, it will be the remaining space, which will be from 0x80,000 to 0xFF, FFF. Now, an important thing to note is that if we're splitting the address space into exactly half, we could use just the most significant bit to decide which device is actually being accessed. So that would mean that in the addressable space, if the SRAM is here, addresses go all the way up to 0x7FF. That means address bit 19 is going to equal 0 for all the addresses within that range. And then all the addresses within the range of 80,000 to 0xFFF will have the address value, the address 19 bit equal to 1. So we can use that as the switch. If address 19 is equal to 0, we connect it to the SRAM signals. If address 19 is 1, we connect it to the peripheral on external bus signals. Now, so the first thing you probably want to do is to update the NEOS system. So the only thing that needs to be changed here is the size of the bus bridge from 512 kilobytes to 1024 kilobytes. Okay, so as you can see, the addressable space has increased, but now there is memory overlap, which we can fix by just assigning base addresses again. Okay, so what we probably also do is save this as a different QSys file. So we'll save it as Neos System 2. I've already tried this out before, so that's why it's there. So we'll save it as Neos underscore system 2, and then we'll need to generate it. Okay, so you can look at this HDL example to make sure that nothing has changed. So all the internal port signals remain the same names. The only difference is that it is now Neos underscore system 2. For the top level module, I've taken the Lab1Part3 top level module and then just added in the ports and instantiations from Lab1Part1. So I've added back in the switch and the hex displays and their associated port declarations. As you can see, the Avalon bus signals remain mostly the same. The only difference is that I've changed the address wires from being 18 to 0 to 19 to 0 because we have a double in the size of addressable space. For the bus enable signals, now there will be one bus enable signal coming out of the Neos 2 system, which will need to be split to going to either the SRAM, so there's a bus enable SRAM signal, or to the peripheral, so there's a bus enable peripheral signal. Similarly, there is an acknowledge coming from the SRAM and from the peripheral, and a read data coming from the SRAM and peripheral, which need to be selected and connected to the one acknowledge and read data that is going into the Neos system. So I've created some logic down here which does that, and they're all just ternary statements, dependent on the address 19 bit, because as I said before, that will determine which half of the space that you are trying to access. So for what we said was that when address 19 is 0, then we wanted to access the SRAM. So the bus enable signal is ANDed with address 19 to give you the bus enable of the SRAM. And for the peripheral, it's the opposite, where address 19 is 1 and bus enable is 1. Similarly, for the acknowledge, if address 19 is 1, we want it to select the acknowledge coming from the peripheral device. And if it's 0, we want to select the acknowledge coming from the SRAM device. And the exact same thing is done for read data, but obviously using the read data signal and the read data peripheral and read data SRAM signals. So the Neos system instantiation is exactly the same, except now we're using the 2 here for the Neos 2 QSys file that we just generated. The SRAM controller is exactly the same in terms of instantiation, except we have bus enable SRAM here. Now, what I forgot to change was the acknowledge should be acknowledge SRAM, and read data should be read data SRAM. Peripheral instantiation is similar, and I should make this peripheral and this one peripheral. And finally, the 7-segment display instantiation is unchanged. Okay, so what I need to change as well is that we're not using Neos underscore system anymore, so we need to remove that QIP file. And I need to add in the new QIP file. Oops. Okay. Make sure that lab10 underscore part 3 is it top level module? Okay, let's compile. Okay, now we can program the FPGA. And if I was to reset the board, what you should do is set the registers to 1s, 2s, and 3s. That's the slave peripheral registers. Okay, now we can open up monitor program. And create a new project. Okay, now we can compile and load. Okay, just to show you what the assembly code is doing, it's just a combination of the part 1 and part 2 assembly codes adjusted for the address space, the new address space. So the SRAM section just loops through and does a store word, or a store half word and a load half word to each half word address within the range from 0 to 7 FFFF. And then for the peripheral section, it starts at 0x80,000, and then I have just stored the addresses at each quarter, which start each of the different slave register address spaces. And then that just does a store half word and a load half word from each of those. Okay, so let's go back to monitor program. Okay, so as we step through, the addresses get stored into the registers, and then it starts writing values to the SRAM section. So if we go here, we can see that it's written 0 and then 2, and then the next one it should write is 4, to that half word, and then 6, yep, and so on. So that will continue through all of the values up to 7FFFs. So this should be the last address, and then the next one starts the peripheral registers. So what I might do is go back to disassembly and put a breakpoint at the beginning of the peripheral section and just run it through to the breakpoint. Now if we go back here, you'll see that all of the values are just incrementing by 2 for each of the sections all the way up to here. Okay, now the next thing that it will do is it will write the value. So once it puts in all the addresses, okay, so it's first going to store to register slave register 0, and it will store the value in R8, which is 1, 2, 3, 4. If we go back to here, we can step over to see that 1, 2, 3, 4 has been written for every half word, or to the slave register 0, which maps to every half word within the first quarter. We can also see that on the D2 board, slave register 0, the hex displays is showing 1, 2, 3, 4. Now if we switch over to slave register 1, and step through, you can see that now it writes 5, 6, 7, 8. We can also check that in the memory window by going to press A and 4 zeros. Okay, and then you see that from after the boundary, it starts 5, 6, 7, 8 in each half word. The next one I think was C and 4 zeros, which is slave register 2. And as you can see, it has the same values. And the last section was that writes the EFF. The other thing that we should be checking is that it reads it back. So the load word should read it back into R14. If I step over that, it reads the value back into R14. Okay, so that's what we should be looking for the assembly to test it out. We didn't include the other transactions in this because we assumed your code is either correct from part 1 and 2, or you have used the solution code to then add it to do part 3. So all we're really checking is that the mapping has worked correctly